Good morning. Last two classes we talked about diffusion in solids. We learnt about the laws that govern the process of diffusion, which in reality is a process of mixing. We derived certain expressions. We looked at looked at expressions that describes the concentration profile in a diffusion couple. We also looked at in detail about the possible mechanisms, and what we find that vacancy plays an important role, and it is generally believed that most of the diffusion is aided by vacancy. And although we derive number of expressions based on the laws governing diffusion, let us look at it. Unless we solve some numerical example, often it is not possible to get a deeper insight into the subject. So, I thought this class we will take up few numerical examples, and we will try and solve these. So, this is in short what have been covered in the last couple of classes. Now, let us look at problem 1. Here we try and find out a correlation between melting point and diffusivity. Now, here the problem is stated like this: the melting point and crystal structure and diffusivity in terms of these two constants d naught and q, which is a molar activation energy, are given in the following table, and estimate d at a given temperature and plot d versus melting point, and try and see what can you conclude out of this. So, this first table, it gives us a set of metal: copper, silver, lead, aluminum, nickel. They all belong to face centered cubic structure. They all have face centered cubic lattice. As melting points are given in degree centigrade, mark the unit, and here the d naught, it should be d naught d suffix 0, and this dimension is meter square per second, and the activation energy is given in kilojoule per mole per degree Kelvin. And what you need to do, you know that d is given as d naught exponential q over r t. So, you can set this calculation very easily in a spreadsheet, and what you can do, you can write the expressions over here and then estimate d as function of estimate the d for a particular temperature. So, for individual, in any case at a particular temperature, let us say we calculate d at T equal to, let us say, 100 degree centigrade or room temperature, and try and see does this have a correlation with the melting point of the metal. And this table gives the melting point here, of course, mark this is degree Kelvin of BCC metal: tungsten, vanadium, chromium, niobium, moly and alpha iron. This is the melting point, this is d naught, and this is the activation energy in kilojoule per mole per degree Kelvin. So, here you can write, fill up this with d calculated using this expression at a particular temperature. Now, you try and plot this. First, let us look at, this does not involve any calculation, just make a plot, that activation energy with melting point. Now, this is for FCC metal, this is the line, trend line. So, this is for the lowest, possibly this must be lead, and this is the highest, and look at this linear trend. Similarly, this is for BCC, and but if you extend, say suppose here, if you try and extend, what you can see that if there is any element or any metal which exists in two crystal structure, say FCC and BCC. So, one example is iron, and possibly most likely this represents iron. So, iron exists at high temperature as a face centered cubic structure. So, if you extend it, you get a diffusivity, self diffusion coefficient of iron in FCC lattice, which will be somewhere here. If you can extend, and maybe this you can try and estimate this and verify. So, in the same way, what you can try, we have just seen that activation energy, this is a function, or this depends on crystal structure, it depends on crystal, and it also depends on melting point. Now, you can try and find out, is there a relationship, similar relationship between Q and latent heat of melting. Latent heat of melting. Next, if you calculate diffusivity at say fixed temperature, possibly I think 100 degrees centigrade, and look at this plot, the diffusivity and melting point. So, that means if the melting point is higher at a given temperature, its diffusivity is lower. So, look at this. So, if for a metal melting point is low like lead here, its diffusivity at a fixed temperature, say room temperature or 100 degrees centigrade. So, here you see this has the highest diffusivity, and this also is a function of the crystal structure. So, look at BCC. So, that means diffusivity in BCC, you can say if the same metal exists in two different crystal structure, you will find the diffusivity, self diffusion coefficient in BCC is higher than that in FCC. This is primarily because there is more open space in a body centered cubic lattice. So, these are the two conclusions which are quite important, and this often helps you to determine the diffusivity, to know about diffusivity of metals where the data are not available. Now, let us look at another problem. This is a problem on Kirkendall effect, and we have seen that if you make a take a diffusion couple and then you put a marker, now often the diffusivity of the two metal may not be same, maybe diffusivity of A is greater than diffusivity of B. In that case, more number of A atom will move in this direction than the number of B atom moving in this. So, obviously, what will happen, this interface will move like this, the marker remain constant. So, so what you see here in this case, if you draw the concentration profile, you will possibly get a profile like this, and you say let us say that this is the Matano interface. Matano interface is the one where this area and this area, they are equal, and the marker position is this. So, there will be a gap between this Matano interface and the marker. And here is an experiment which was say suppose an hypothetical experiment has been conducted with the two metal A and B, and here is a marker placed over here. Now, in this diffusion experiment, it has been found that the marker between the two metal moves through a distance of 0.0144 centimeter in 200 hours with respect to Matano interface. So, here this is the Matano interface, this is the concentration profile, this area and this area, the two are equal, and this is the position of the marker. So, now this is this distance in 200 hour is of this magnitude. Now, if interdiffusion coefficient for atom fraction A is 0.4, at A equal to 0.4, that is atom fraction A equal at a particular point, say this is the concentration line, say atom fraction 0.4 somewhere here, let us say. So, at this point, that interdiffusion coefficient is given as 10 to the power minus 7 centimeter square per second, and slope at this point is 2 per centimeter. Then estimate the intrinsic diffusivity of A and B. Let us see how do you solve this problem. Look at this what is given. So, this is let us try and calculate what is the velocity with which that marker moves with respect to the Matano interface. In fact, the markers are stationary, it is actually the Matano interface which is moving. So, if you calculate this velocity delta x over delta t. So, delta x is this is the time in hour. If you want to most of the cases we calculate velocity, try to calculate in centimeter per second. So, you convert this hour to second, then it comes out to be 2 into 10 to the power minus 8 centimeter per second. Now, we know that interdiffusion coefficient is equal to the mole fraction. So, mark this difference, the mole fraction B times the intrinsic diffusivity of A dA plus N A times intrinsic diffusivity B. So, this is one expression and this is given. And now, the velocity of the marker is actually, we have derived this expression, is given as the difference between the density dA minus dB times this concentration gradient. So, del Na del x. Now, this magnitude is given, the estimate of this slope of this plot, this is the concentration, this is the distance, slope of this concentration profile at mole atom fraction 0.4 is given. So, therefore, you substitute it here. So, what do you get? You get this dA, this is 2, it is given, and this is equal to this. So, therefore, what you have dA minus dB equal to 10 to the power minus 8. Now, look at it over here, you have one equation here, and also Na and Nb, if you add them together, these are atom fraction and it is a binary system, this is equal to 1. So, therefore, you have 3 equation, 3 unknown. So, you can solve it easily, and I leave it up to you to do this to derive or to actually estimate the numerical values for dA and dB. Now, the third problem we will look at the Matano method. Say Matano method is very commonly used to find out diffusivity in alloys, and we have seen during the lecture that diffusivity is actually a function of concentration. Say diffusivity, it's a function of the concentration. Say in a binary alloy. So, this is not this is not a constant. This is not constant. It is a function of the composition. So, that is why this this diffusion equation, when you try and solve even in a say one dimension, we treat it like this. So, this is so now Matano method, it is a procedure which will help you to estimate D from concentration profile. So, if you look at the concentration profile, so if you assume D to be constant, this to be constant if you assume, then you will find that these profiles, they are this profile, they are symmetric. So, this is your initial interface between A and B, and after a time t, say let us say t after say 100 hours, you get a profile like this. If you assume D to be constant, then this profile, it will be symmetric on either, it is symmetric about this interface between A and B, and this area and this area will be equal. But in most cases we will find that this is not symmetric, and which indicates that this diffusivity, or which is called as interdiffusion coefficient, is actually a function of composition. Now, here is an expression, here is an example, and if you try and solve, you will get a feel about the procedure. Now, this concentration profile in a diffusion experiment conducted on a couple consisting of metal A and B is given in the following figure. Look at this figure. Here, you know, this is not symmetric, even if you consider that this is the Matano phase, where this area and this area they are equal, area may be equal, but the curve is not symmetric. So, this indicates that in this case, looking at this concentration profile, it is possible to conclude that diffusivity in this case, this interdiffusion coefficient in this case, is going to be a function of composition. Now, suppose this is the concentration profile at time 50 hours, then calculate D as function of composition. Now, if you recollect the procedure, we have seen that with just substitution of variables, say basically that eta you substituted that the variable that we transformed is is eta, which is x over root 2. If you do this conversion, then this partial differential equation gets converted into an ordinary differential equation, and it can be and its solution, it is possible to arrive at its solution, and which is listed here. Look at this, this is integral x dc, x is the distance and c is the dc, c is the concentration. Now, here in this concentration profile curve is here, this axis, y axis is the concentration, this axis is the distance. Now, to find out, to locate that Martano interface, what you need to look at this concentration profile and select a place where you find that this area and this area is constant. That means, you try and find out this area. Now, here look at this, x has positive, this side x is negative, this side x is positive. When you calculate this area, this portion will come out to be negative and this area will come out to be positive. Add the two, you will get, it will be 0. So, that means, this integral equal to 0 describes this line. Now, to find out the diffusivity, what you have to do, you have to again find out this area 0 to C. Say suppose this concentration is at this point, that means 0.4 or 40%. Say suppose this is that 0.4 line or 40% line here. So, you have to find out this area. Now, area can be found out easily using Simpson rule or graphical technique, and it can very easily be done in a spreadsheet if you enter this concentration as a function of distance. And once you find out this area and look at the and this slope, then you have to find out slope at this point. So, draw a line over here, draw a line over here, and this also, if you have the tabulated data, it is very easy to find out slope at any point. Now, once you find out the slope at this concentration C, here you find out the slope, this is known, slope at concentration C, the T is known. So, this part is known. So, therefore, the interdiffusion coefficient can be estimated, and this solution can very easily done in a spreadsheet, and which is shown here in a spreadsheet. If you enter say suppose this is the concentration profile, this is the Martano interface. Now, take a small element here. So, let us say that this is a concentration, say C 1 here, C 2 here, and this difference is very small. So, in that case you can approximate the area of this by multiplying this distance delta C with the average value of the distance. So, distance also you say this is x 1, this is x 2, say suppose average of this 2 is x 1 plus x 2 by 2. So, this is the midpoint. So, if you look at like this, what you are actually doing, you are making an approximation, all right, but if your element that size is small, the mistake is very little. So, what you are doing is here you are drawing a line midpoint and assuming this to be the area. So, here you are ignoring this, but this is the additional. So, in a way you can say this will give the approximate area, and which also can be done very easily if you enter the data on the spreadsheet. Now, look at the spreadsheet, you enter the data composition, percentage composition, this is the delta C change in composition. So, I mean the composition has been estimated at equal interval, it seems. Say it is every element, you know, this composition changes by the same percent, 6%. Then you can find out average of this distance, which is listed here, and then you can find out the area, and look at here you have found out area almost up to this point, and you can add that area. This is the area of the small element, say somewhere here, next one will be the next element. So, this is how you can set up your spreadsheet, and you can sum all this and you get this area. Now, same thing you do for that entire concentration profile, and here you see if you add up to this, that is 5 point, area is 5.81, and you add this part here, it is this. So more or less you can see that the location of that Matano interface is correct. The area, this is plus almost of same magnitude, it is negative. So, net area is 0. So, therefore, that means the Matano interface location is all right, and now you can try and find out the slope of the plot. So, you just divide delta C, we have found out delta C. Similarly, you can find out delta x as well, and the ratio of the two, it gives you the slope of the plot, and then you can get and when you calculate this area, you have to calculate, ignore that negative sign. So, because the total area gives you that amount of mass transport. So, mod area, modulus of that area which is listed here, then you can sum the area, and summation has to be from the concentration 0. So, if you go back, summation has to be from this negative end, area from here up to this, then this area plus this area plus this. So, that way you have to estimate all along the distance, and which has been done, and you can and after having done this, then you can calculate diffusivity, and diffusivity is calculated using that expression. Look at this, here you have calculated area at up to a different compositions, this area is known. This also, the slope of the plot also has been determined, and the time t is given 50 hours. So, substitute that time t as 50 hour, and then therefore, it is possible to calculate that interdiffusion coefficient as a function of distance or composition. Having done this, now you try and plot, and what you find here is that interdiffusion coefficient is a function of composition. So, these are the intrinsic that diffusivity. Similarly, here also there will be an intrinsic diffusivity point somewhere here, but in between this interdiffusion coefficient, initially it goes down, then again it goes up. So, this is interesting. Look at it and try and let us look at it little more carefully. Now, when we derive that interdiffusion coefficient, the darkened expression equation, you will recall that interdiffusion coefficient was derived at N b times diffusivity of A plus N A times diffusivity of B. Now, here if we know that N A plus N B equal to 1. So, if you substitute this, what is the type of variation do you expect? So, in this case, say suppose diffusivity, intrinsic diffusivity d A is over here, this is the other one. If you follow this, then the interdiffusion coefficient should be given by this line, and which is very evident from look at this expression. So, this is the interdiffusion coefficient for this N b. So, this is d minus d b. So, which clearly comes out here d b times 1. See and this is this d b, you take it out, it goes that side. So, it it comes out to be d minus dB. d minus dB is this, and this portion is dA minus dB. So, therefore, what it shows that this point, this line should be linear, but what we actually get over here is something like this. And why do we get it? This is because when we derive this expression, we make some implicit assumption, and that assumption was that system that the two A and B, metal A and B form ideal solid solution. That means, A and B, that system, binary system, is an ideal solid solution. Now, in an ideal solid solution, we say that actual local concentration or activity, what we say that in thermodynamics we define a term called activity, which actually means activity A, which means effective concentration of A at a particular point, and this we assume that this is equal to atom fraction A. So, that means it follows a law called Raoult's law. So, at any time, so if you have A and B atoms, at any time number of B atoms surrounding A will be exactly equal to that given by the composition, that derived from the composition. But very often this kind of ideal system is non-existent. Many times we will see formation of cluster or formation of or some kind of a ordering. So, in case if it is a cluster formation takes place, then what happens is activity of A is greater than in A atom fraction. That means, a cluster some locally that concentration of A will be higher than actual atom fraction of that particular alloy. Similarly, if there is an ordering, in that case A will like to have B as its neighbor, I mean that will be more preferred. In that case, this will be less than N A, and similar thing is happening over here. So, therefore, we get a concentration profile like this. So, that means the system we just described, there is a tendency of ordering, and that activity, that is local concentration, is lower than what it should have been. Local concentration of A is lower than what should have been. So, therefore, what we need is another correction factor, which we call a thermodynamic correction factor, and this is defined over here as an activity coefficient. And this in thermodynamics, this has been worked out in detail, and maybe you can refer to course book on thermodynamics for this derivation. Now, we have during the lecture we have talked about the actual process of diffusion as one of random walk. Now, let us see is it possible to simulate the movement of atoms. Say I will solve a case for 1D, and if it is possible to solve it 1D, the method is given and you can take it and extend it to 2D and 3D, because 2D and 3D it will be little more computer intensive. So, I am giving say one particular case which is solved over here, and here we are trying to simulate a 1D diffusion as a random walk process. Say suppose initially an atom is here and one step, suppose what happens on the next time step, it can either move say one step forward or one step backward, and this is defined decided randomly, and this goes on with time. Say after some time, say suppose after one time step, if it comes to occupy here, next again it has to be a random choice. So, it can move here or here. If it comes back, then it remains in its original position, and this process continues, and this can be easily simulated in a computer, and most of this and even in a spreadsheet. Normal spreadsheet provides a random number generator, and here is an example which has been solved using electronic spreadsheet, and these instructions which are given here. They consider 1D lattice, simulate diffusion as random walk along positive and negative direction with probability equal to 0.5 each. Now, find the mean distance covered and standard deviation as function of number of steps, and compare the results with normal distribution. Now, you can set up a spreadsheet like this, say construct a matrix X, these are two suffix say t and n. T represents time, n represents let us say number of trials, n is the number of trials, and this is the time step. So, now here we say that number of trial is we put in columns A, B, C, it continues up to n, let us say, and here each time step. So, we can number each of these column as 1, 2 up to n, and this is your initial position. Every trial, so this is the first trial, this is second trial, third trial, nth trial. Every trial initial position is the 0, that is center, and then it goes on changing. Say here it goes to -1, here it is +1, here it is -1. So, that way it goes on continuing up to time t, and then what you can do, you can find mean of say after what is the most likely location after the first time step. You can find out its average and its standard deviation, and you can do the same for each time step, and this can be easily set up in a spreadsheet. Say suppose Excel has a function as a random number generator, which is RAND, is a random number, it is a pseudo random number, it may not be exactly perfect, but still in many cases it simulates quite well. So, and now before using, you set this calculation mode to manual, because every time you enter a data in Excel, it recalculates every cell, and then use the F9 key to recalculate. After you have entered the data, use this. So, this is the first initial setup you have to do. Then put a set row 0 in row 2, and this represents that initial set. Then update all cells down below this 2 using this expression. This expressions can be entered and copied. So, this is will be A2 plus you give a conditional statement that if random number is greater than 0.5, the random number generator generates random number between 0 and 1. So, if you say that if it is greater than 0.5, that means the probability is half basically. So, in that case if it is greater than 0.5, then it goes to +1 direction, that means you will add 1 to this. If it is less than 0.5, you will subtract 1 from A2, and this is how each of these cells you can copy this formula. You can copy in each of the cell say down below. So, formula which is entered in all this cell is exactly same. Now, use Excel also provides average and standard deviation as a standard function. So, you can fill up the column for mean and standard deviation, and now you can generate do that solve and generate, look at some of these plots, that standard deviation. You will find that standard deviation it is rather insensitive. Number of trials whatever you do, it always follows a definite curve, whereas the distance covered may not. You can go on and say like previous one here, and this is a parabola, and if you plot standard deviation square, you get a straight line, and look at the slope is constant. The slope is constant. Next, its mean position, it keeps on fluctuating here. So, and in fact, this is not same. You repeat the trial number of times, maybe this plot after say 1000 step, say here it is located over here. Next time you do, you will the plot will not be exactly same, but does not matter. What is more important is this particular plot, and why? And the reason lies in the nature of the distribution that you get. Now, Excel also provides some standard functions called which you can array functions, and which you can use to calculate the frequency distribution. So, this frequency distribution, what is? You can set up a bin. So, bin means say let us say that position is the bin where it is. So, this is a mean position, say suppose this is mean somewhere here is 0, minus 5, minus 10, something like this, the location, this is plus 5. You can set up a bin, and then you here you enter this frequency function over here. Frequency function, it will ask for the bin, you define the bin, you define array, you define bin, define array, and there is a logical variable. If you want to determine the frequency, whether it is cumulative or probability, that distribution function, you can put either a 0 or 1. So, I do not remember exactly which one, but when you enter this, you have to mark that whole area, paste this function, and what you have to enter, when you enter, just do not press just the enter key, then entire array will not be entered. You put control, shift, alt, you press 3 and then enter. Then entire array is entered, and this is what has been done here, and that entire data has been divided into different class intervals, and this is the frequency distribution. The blue one what you see is the simulated, and now you can easily calculate the mean and plot that normal distribution. So, it shows that this trial, this distribution function is very close to the normal distribution function, and in a normal distribution function, that one important factor is the standard deviation sigma, and this standard deviation we have found that this standard deviation is actually is proportional to, in this particular case, root over t. And we also have seen that the diffusion distance also proportional to root t, and this, so that means here is also a concentration, here is also a proportionality constant, here also there is a proportionality constant. So, these two proportionality constants they have a relationship. So, basically both will be identical. So, what it means, if you go back, this slope is actually give you a measure of diffusivity. So, with this I hope you had now a fairly good idea about diffusion, solving some problems in diffusion, and what we have tried to show you today is tried to solve a few problems, and one problem which we have taken while during the lecture, that is the determination of concentration profile, and we have looked at 1D solutions only, and many of the cases of our interest we will be looking at. A 1D solution itself gives you a good insight into the material behavior and transformation processes, but you can extend it easily to 2D and 3D, and maybe in this try and simulate this random walk process to a 2D case. Now, in a 2D what you need to do, in 1D we have seen that a point is here, it can go this one step this side or one step this side only. So, the probability is half, moving probability of moving this direction is half, or probability of going to this position is half. Now, if you extend it in 2D, so 2D what you have a grid. So, you have a point here. Now, this point it can move here, it can go here, it can go here, it can go here. So, this means the probability of going in a particular direction is 1/4. So, here also you can consider an array, and then you can set up your that spreadsheet, the calculation in such a way that you use random number generator, and random number generator generates number between 0 and 1. You group it into 4 groups, say 0.25, 0.5, 0.75 and 1, and you can set up this. I leave it to you to set it up. So, if it is say suppose 0.5, it goes from here to here. If it is if it is between this and this, then it goes here. If it is between 0.5 to 0.75, it goes there, and if it is 1, it goes here. So, what it changes, say every point in this particular case, one cell could define every point, and in this case you have to set up x and y, both coordinates x and y. So, you will have different combination of x and y. 0 0 is your start. So, next is it could be 1 0, it could be 0 1, minus 1 0, 0 minus 1. So, you have these 4 options, and this can be repeated, and this is how you have to update, keep updating these two fields together. So, and I will leave it up to you to tune this spreadsheet and simulate 2D, and if you are satisfied with this, you can extend this to 3D as well. Now, in 3D, this probability of transition, there will be 6 position. If you assume a simple cubic lattice, visualize simple cubic lattice, in that case there are 3 axes, and on each side 1 point. So, this probability will be 1/6. And in that case you will have another coordinate x, y and z. So, with this I think we cover our lecture or finish our lectures on diffusion. Under this we looked at the process of diffusion, and it is a method of mixing. We have also seen that if you assume that diffusivity to be independent of composition, you get symmetric concentration profile, and but in most cases in reality you do not get a symmetric concentration profile, and this interdiffusion coefficient, they are function of composition, and we derived an expression for interdiffusion coefficient for an ideal system. And we also have solved some cases where in ideal cases you get a linear dependence, but in most cases you do not get a linear dependence of concentration dependence of diffusivity. So, in that case you have to adopt. So, if you want to model this, you have to bring in thermodynamic factor, and we also looked at mechanisms of diffusions. We learnt about several experimental techniques by which can be done to find out diffusivity. Simplest is the diffusion couple, and the simplest way of finding out concentration profile is take a section and then take the filing, do the chemical analysis, and this is how most of the data, diffusivity data, have been collected. And in case if you do not have diffusivity data for certain material, it can also be calculated from the data available for similar material. You have to look at, there is a correlation between diffusivity and melting point, and it is possible to calculate from the available database and thermodynamic database can be used to calculate diffusivity. Thank you very much.